LangChain has an incredible caching system laid on top of the large language models that you use it with. The resources on this though are pretty scarce, and as of this recording, many of them are still outdated. If you search its official documentation, you'll see that it still uses the old .predict method, and if you try to run it, you get issues like this. Basically doesn't run. So I did a quick Google search and checked the first two results, and they are just lazy copy and paste from the docs, which means it's also wrong and it plainly doesn't work. But caching is so useful, especially if you're building LLMs for production use where you're feeding a large context to the model, like using GPT to query your own personal knowledge base. I have a video on exactly that, where I load in my bullet journals in a markdown format and I build my query engine using GPT on top of it. Or if you're trying to learn a foreign language by getting GPT to tutor you on a book, I also have a video on that. Now in both cases, you're feeding a large context to the model and you're going to incur quite a bit of cost, and your queries will be slow if you don't cache. So let me show you how to do caching with LangChain, and it's surprisingly easy. All of this code will be on my GitHub along with the rest of this LLM series if you've been following along. Now we're on video number 13, so there's a lot that we've covered, and caching is just a great addition to your LLM development toolkit. So hop over to GitHub, do a git fork, and then do a git clone, and then all you need to do is to just follow along from here, and I'm just gonna name it demo 14.py. If you want to watch the entire series from the top to the bottom, you go to the GitHub, there is the readme page, and you can just follow along, pick the one that you're interested in, and just follow along, alright? Now once you have an empty file, you do the same thing. You see me do this over and over again, and if you've been watching this series, you probably get bored of this part already. So we bring in LangChain because we're going to be using LangChain. We want to bring in our environment variables, and the way I prefer to do it with .env. So from .env import load.env. Then what I like to do is like immediately call it. So this will look for a file called .env file, and it's gonna read in all the variables for there. So this makes it a really viable way to maybe store your environment variables, your OpenAI keys, and all of this stuff. I also want to be, apart from LangChain, I want to be using LangChain.LLMs import OpenAI. Now typically you use something like GPT-4 or GPT 3.5 or 3, but to make caching a bit more obvious, to see the benefit of that, we're going to use a slightly older model, a slightly slower model. So I'm going to have my LLM, instead of GPT 3.5 or 4, we are only going to be using, let's model name, say text, Da Vinci. You can go 003 if you want to. I'm going to stick to 002 to make sure that it's a little bit slower. It's a bit of an older model. So this gives us a bigger contrast when we look at the pre-caching solution and the post-caching solution. Now the first caching mechanism is the in-memory cache. So let's bring that in as well. So from LangChain.cache import in-memory cache. Alright. So this is the cache that stores things in memory. So let's initialize that. I'm going to say LLM, actually bring this in, and I want to say LLM cache, and that is just going to be the in-memory cache. Just initialize that. Now LangChain also has a hook to hook into this OpenAI callback in order to get things like how much does it cost you, how many tokens and stuff. So we're actually going to be using that as well. So we want to see, right, the pre-caching solution without cache, how much is it going to cost, how much tokens is it going to consume, and then with the cache on, right, what kind of a difference does that make? So let's go ahead and say from LangChain.callbacks, and I'm going to bring in get OpenAI callback. And this is a context manager, so you use it as such. So you say get OpenAI callback, and you can call it anything you want. I'm just going to call it CB, stands for callback, and then you can just say result equals to LLM, and then you just pass in a question. So for example, I could maybe just a simple one. I would say what doesn't fall far from the tree. Alright, you can ask it anything you want obviously, but I'm going to just do that and I'm going to print the result. And this is kind of it, a quick introduction to all of caching if you want to stop here. But I want to go into the details about how this works, and I want to show you comparison between pre-caching, post-caching. So stay with me for a bit more, but to make things really clear, I'm also going to print the context manager, which is the CB. This is just a callback, right? You're just going to print C. You can call it context, you can call it context manager, whatever, you can just call it CB, just stands for callback. I want to bring in the time so that I could time the cache solution and the pre-cache solution. So instead of just the result, we're going to have start. I'm going to create a simple time. You could also just use the decorator and just time it and then write the decorator and stuff. You can also do that, but I'm just going to keep things really simple right now. Then I want to have my end time here. So time equals time as well. I'll just print a few lines. This is the callback. And I want to append the result of this difference between end time and start time. So if I take this time minus the start time, the end time minus start, it tells me the elapsed time, meaning the duration of which this function is running, right? So I want to actually append that string. So I can only append strings if they're both string. I can't just take this and then append stuff. So I need to convert this to a string first. So let's do that. And then I'm going to convert that. And then now I can add my string. So this is what I would do. I'll say n minus start. Not start minus n, because that wouldn't make sense, right? This is the final time. This is the finishing line. This is the starting time. And make it 2 decimals or whatever, 3 decimals, up to you. Then I want to just say seconds. That's all. And there we just implemented a very simple caching mechanism. This is the in-memory cache. Now I'm going to put a pause here and say, if you have interrupted me at this point and you ask me to explain how in-memory cache work, I'm going to just take a guess and say that it's going to be using Python's LRU cache, the least recently used cache, right? That is also part of the standard library. And I love caching. I have a video on LLU cache if you want to introduce some built-in caching to your own Python programs, so you can go and watch that video. But I took a look at the code and I realized I was wrong. It was actually far simpler than that. It doesn't even use LLU cache, it's just a dictionary. So as a quick primer, a cache is just this dictionary that stores the result of a function call, so that repeated calls with the same arguments, they don't have to recompute the result. It doesn't have to call the function to recompute it. So if you have a function that takes a long time to run, you can cache the result of that function call, and then the next time you use the input, it should yield the same result, right? The same input should map to the same output. You just have to refer to a dictionary, do a quick lookup instead of having to burn your OpenAI credits and your computation power and whatever resources you're using for the computation. It saves you lots of time and money, and if you're not using cache for all of these repeated queries, I think you're leaving money on the table. Now we are ready to run all of this, so let's go ahead and actually just do another one here. I'm going to show you really quickly why I would do that. I'm going to re-execute this stuff. I'm going to call it CB2, then I will put this as CB2. I will not want to override the results, so I'm going to have this as result 2. In fact, I'm going to have result 3 as well. Right, I'm going to have print result 2, then print result 3. So notice that this is actually very identical. I'm just calling it double, triple, and show you what this in-memory cache does for you. Alright, so let me save all of this. I'm going to go and activate my environment and clear the screen, and I'm going to say that Python demo 14.py. And just to run it in iterative mode, I'm going to put -i, run it. Alright, let's take a look. And it started from here. The expression that doesn't fall far from the tree is used to describe someone who has inherited their traits from their parents. And then this is the CB, this is when the result is printed, then it runs this. This is the callback. Now it says the first time, right, this is the first time it's running. Notice this is the first time it's running. I've used 37 tokens, I've used 9 prompt tokens. So 1, 2, 3, 4, 5, 6, 7, but doesn't become does not, you know, so like there's a small details here, but also maybe there's a bit of a context, so those also count. And so that this is prompt tokens is 9, this is because the prompt is really short. Then the completion is token 28, so if you were to count this, and then this is not exactly 1-to-1, so it's not like 28 tokens means there's exactly 28 words, but you can see it does use some tokens. Sum them up, 28 plus 9, you get 37. And how many requests does it make? 1. How much does it cost you? 0.00074, and it takes 0.8 seconds. Now all of this is because you wrote this time function for yourself, right? Then we go into the second time we call it, and then the third time we call it. So the second time and the third time. The expression that doesn't fall far from the tree. Now realize that the result is the same. So when I pass in the same input, instead of actually recomputing that, it doesn't recompute it anymore. Why? It doesn't have to use your completion token. It said, hey, this is I've done this before, I'm going to give you the same results. So that's the first observation, is that it doesn't recompute, it just gives you the same stuff. Then let's take a look at the second observation. It's that if you were to look at the context now, the callback now, you see that the token uses 0, the prompt token uses 0, and the completion token is 0. And this is the same for as many times as you want to call it. So you can keep repeating this query now, but it doesn't cost you any more money, it doesn't cost you any more seconds, it doesn't cost you any more tokens. All of this is free now. Why? Because it doesn't even make the call. It consults the dictionary. It says that there is a dictionary, there is a key, there is a value. The key is what doesn't fall far from the tree. This is the value. I've computed that, I've stored them in the dictionary. So when you keep asking for the same thing, I'm just going to refer to the dictionary and return that result back to you. So it doesn't have to go and consult that and then regenerate this response for you. So that's really cool, right? That's really simple. And this is all just using the in-memory cache. Now, of course, you can take this a bit further. I'm going to go ahead now and bring in this in-memory cache. I'm also going to bring in SQLite cache. So I'm going to show you this. There is also SQL Alchemy, but I'm going to use SQLite now. So I will try to hide this. Actually, let me duplicate this, and I'm going to hide this. And I'm going to change this to SQLite. Go in here and say, where do you want this database be created. You can name it anything you want. The documentation will tell you to name it something like LangChain.db. You don't have to put it as a hidden file, but you can also have it as a hidden file, so let's say .chain.db. That work. If you don't want it, you can say SQLite, that also works, doesn't matter, right? So just name it something that you can find in your local directory. I'm just going to give it a temporary place, and this is just going to be .langchain.db, and later on we can delete that. Maybe you can add a note here to say that you want to remove .langchain.db if not used, or git ignore it. Alright, so this is a good place to just go to git ignore and just add this so that it doesn't get committed to your git. We'll go ahead and quit out all of this. I think that's the only two things we need to change is to just add SQLite cache and specify that into a SQLite cache and put a database path. And so if we were to run the same thing, and sure enough, it got created, langchain.db, and now it says here, right, initially when you first run, again, it takes the same thing, 49, 9, 40, and then there is a 0.8 seconds, close to 1 second, costs a bit of money here, successful request, but now it costs 0, 0, 0, 0. And then because there is a database there, it adds a bit of overhead, but that's 0.01 seconds, who really care about that kind of a time difference? So if you want it to be absolute speedy, really, really fast, and you have the kind of memory to store it, and you're using it in an ephemeral style, you don't care that they're persisted somewhere, then just go ahead and use the in-memory cache. It's probably going to be slightly cheaper because you don't have to do the I/O between the DB and your actual working memory, right? But if you actually want something more persistent, you want to save them into a DB and you can open up new sessions later, you don't want to lose your stuff just because you put into a different machine or something, then you want to use DB. It may add just a slightly small overhead, right? It's still a lot faster because this was 0.86 seconds, this is 0.01 seconds, alright? So in most cases, this wouldn't make a difference. But you will see that it takes no tokens, doesn't cost anything, and costs you no money. Alright, so that's really sweet. Now, LangChain also has a way for us to selectively cache certain sections of our LLM chain. Suppose we have a map-reduce chain where we have a body of 100 paragraphs. We want to map each paragraph to a summary, and then we want to reduce the summaries into a single consolidated final summary. Alright, so this is kind of the use case for map-reduce. The map part of this chain is the part that could take the longest, so we can cache this part of the chain. So map basically says take this LM function and apply it one by one to each paragraph. We have 100 paragraphs, right? So apply it to each one of them, but then do so in parallel, right? Now that you have 100 summaries, now you bring in the reducer. Now the job of the reducer is to produce a summary of this 100 summary. That's the reduce, right? The reducer. It's called reduce because you're reducing the number of summaries from 100 to 1. This is a bit similar to how you think of an aggregation step. If you want to calculate the mean of something, the mean of a population, what you could do is to split your dataset into tenfold, calculate the mean for each one of them, and then take the sum and then do the mean again. That would also give you that, but now you can do so in parallel, right? So the reducer step is typically faster. So you may think, well, I don't need to cache the reduce part. I just need to cache the map part. Alright, so the final summary has a little bit of variance, has a little bit of randomness, maybe the order of the paragraph, maybe different vocabulary, maybe different phrasing and so on. I'll show you in a code how we can do this with LangChain. Let's start off by copying this and pasting that in, and we change this to demo 15. So this is all in my repo. All of this stuff, the books, the audio, we have some exercises where we convert things from MP3 into text, and we transcript it, make the transcription out of text and then do some LM on that. So if you want to follow along this entire series, all of this data set, all of that is on my GitHub. You can follow them along. I'm not going to touch most of this stuff. I'm going to go into the summary.txt. Alright, so I'm going to open that up and I'm going to show you this one. Right? So summary for Australia, summary for Indonesia, and summary for China. All the latest news related to coal mining industry, the energy industry, and it summarized that for me. This is part of a project that we're building for some clients. A lot of my exercises and stuff, some of the data set, I'm going to be using things that are related to my industry. So if you want to take a look at this, go ahead and watch my earlier videos. I have an earlier video where we go into this, where we do Q&A on this stuff. But today is not the day for it. Today we're going to just focus on caching. So just to show you very quickly, there is a section for the summary for Australia. This is a coal and gas market for Australia, and coal and gas market for Indonesia, and the last one for China. So I'm going to close that out. I want to be reading stuff in, and then I want to be splitting them. So I want to use LangChain text splitter, import character text splitter. I will create a text splitter, and that is just an instance of this class. I have an LLM here. I'm going to stick to that, but I'm also going to duplicate this, and I want to create another one called LLM no cache. And here the only difference is that I'm going to turn the cache equals to false. So I have LM and I have no cache. I told you that we can cache certain parts of the whole chain. So this is the map reducer. The map part, I want to be using the one with the cache. So this is the one. And then the reducer part, the reduce part, I want to be using the one where the cache is set to be false. So it's not going to be using any cache. So let's bring in our data. Let's load in some data, shall we? So I'm going to say we've opened, where is the folder? The folder is right here. I have news, and then I have results.txt, I have summary.txt. So let's bring in the summary.txt. I believe even the summary.txt is actually generated with LLM, and this is done in one of my earlier videos, I think 1 month ago or something, 1.5 months ago. So if you want to go and watch the earlier video, you said, how do you generate summary.txt? You go and watch that earlier video, and you come back to this one, and you see how that's being generated. So, alright, so how do you use LLM to summarize a lot of news from Google News, from all these different news sites, put them into one nice TXT, and so you can now query that news. So that's kind of what we did in I think 6 weeks ago. So let's go back in here. What do I name it? I name it summary.txt. So let's put summary.txt. I'm going to create a context manager as well. Then I'm just going to say this on news. I'm just going to go ahead and read the news. And then remember we created our splitter, text splitter. So this is where we could say our text equals to text splitter and just split the text into news. Ideally, this would just create the 3 different parts. To process this stuff into documents, into something that LangChain can work with and can store and can work with, right? We need to bring in another facility, and so let me bring it from here. I'm gonna say from langchain.docstore.document. I believe you've seen this before as well. In one of my earlier videos, I think the video that I did with the journal AI, I said, okay, if you have your own personal knowledge base, you have a set of diaries, and you want to use an LM to query your own diaries and to ask questions, chat with your own diary, chat with your own bullet journal. That's the video I showed you in which I showed you how to use document to create your own sort of chain. So I'm using a very similar technique here. I'm saying, what if the text is too long? I don't want to have have this run for too long. Create a list. In that list, I'm just going to say document, use a list comprehension, and this will be page content equals to T for T in text. Alright? And just to make it a bit more manageable, if this text is really, really long, if you're following along this video and you're using your own data, I don't want you to have to, end up costing you a lot of money. So I'm gonna say maybe just take the first 3, right? Instead of taking the whole thing, just take the first 3. Of course, if you don't care about that, you say, well, I'm so rich, who cares about this stuff? I'm an LM engineer or something. Well, I don't care about this, and just use the whole thing. But I'm gonna be a bit more economical, and I'm gonna say just take the first 3, so 0, 1, 2. And now I'm ready to summarize this stuff. Right? So we're gonna take this and we're gonna summarize all of these different things here. So I don't want to see the entire text here. Let's say it's a really long text. I want to summarize that. So that I could bring in from LangChain.chains.summarizer. I believe it's called summarize.summarizer. Load summarize chain. Then we get back in here and we say chain equals to load summarize chain. Now we just have to pass in look at the signature here. First, the base language model, unit and LLM, and then the chain type. Now the chain type could be one of the stuff, map, reduce, and refine. I think you've seen some of this before over all of my entire series of LLM. I'm not going to go into all of them. But what we want to have now is the map reduce, because we're doing this map reducer, right? We're saying that take each one of this paragraph of text, generate summary, and then reduce everything down into one nice summary, right? So the map reduce paradigm. So first of all, the base language model, let's do that. LLM is the base language model. Actually, we don't need the quotation marks. Then we want to have the chain type. Here, we don't want anything else apart from map reducer. So we only want map reduce. And then finally, we could also specify the reducer LLM. So I said when you reduce the LLM, use the one with the no cache. LLM, no cache. So this is the one here. Alright. So what I'm doing here is quite fancy now. I said, right, run a summarize chain, but for the base stuff, use the one with the caching turned on. So the map will use the one with the caching turned on, but the reduce tab is going to use the one with the caching turned off. And we've seen all of this before, so I guess we don't even need that. So let's remove one of this first. I now have a chain. It's not LLM anymore, it's the chain. So I'm going to say chain, run, and then finally pass in my text, pass in my corpus. And that's my docs here, so let's pass in docs, right? So this is going to execute this onto docs. So of course we can copy this, paste it down here. We could name it CB2. Of course we also want to duplicate this, make it result 2. Alright, so here the first result, and then CB, and then now let's save all of this, clear the screen, and let's run Python demo15.py, and it's done. So let's pull this up a bit and we can read all of this stuff. So it starts off with Australia's coal and gas exports may reduce by half within the next 5 years due to the passing of its peak and the efforts of Asian countries to decrease greenhouse gas emissions. There's a few other summaries here. The seaborne coal market grew by 5.9% year on year to 1,208 million tons. One thing you should do is you should always fact check it a bit. So if you open up summary and you search it up by 1,200 there it is, so 1,208 million tons, so that at least you know the information wasn't randomly pulled from, but it's actually accurate. And then you have the years of frozen relations between China and Australia. There is hope for thaw in the relationship. China's Foreign Minister Wang Yi met with a delegation from Australia to mark the 50th anniversary of bilateral relations and stated that the countries have no fundamental conflicts of interest. Alright, so you can read up more about this. There is also the Indonesian side of summary plans to produce a record 695 million tons of coal in 2023 and export 580 million tons. Again, you should quickly do a quick search into your own data to make sure that it's correct. You could actually prompt engineer to make it more accurate. If you want to learn more about prompt engineering, making sure that there's higher accuracy and stuff, go and watch my other prompt engineering video in which you use something called a guidance and learn how to do this correctly. Actually, I have it here. So this is how you do it, right? So go and import guidance and do it. There is a video dedicated for that. I'm not going to go into this stuff, but there's a lot of other this kind of like techniques that you should learn. So go and watch the entire series. But here, this is the first time it runs. It takes 7.19 seconds. This is not short at all. This is actually quite long, 7.19 seconds. And then it costs you about 6 cents. Alright, so now it starts to cost you a bit of money, right? Because the tokens use is actually getting a bit much, right? The prompt tokens, this is going to be high because you're passing quite an amount of data. And then the completionist token, this is what it costs to generate all of this text for you. So total, it will be 3,262. Alright, that's nice. And this is the first time it's running it. Now, with the caching for the map, right, so no caching on the reducer, but caching on the map side. If we were to implement that, which is the second part here, right, how does it work? How does it change things? So let's take a look. So again, Australia's coal and gas export may be reduced by half and stuff. Cost produced in Australia are in talks. Now you see that the result is actually a little bit different now. So there is a bit of a reliability. Coal producers are in talks with the government of New South Wales following the government's announcement that coal miners should reserve up to 10% of production for domestic supply. Alright, here it says coal producers in Australia are in talks with the government following the announcement that miners should reserve up to 10% production. So this is what I mean by having a bit of variance in the generation of the text. So even though the message is the same, they find different ways to talk about it. And this is because of the reducer side of things. It's not actually cached. So it could generate a bit of randomness here, but the message is fundamentally the same. Coal producers in talks with the government of New South Wales, and then miners should reserve up to 10% of production. That's the same as this. It's fundamentally the same message. It just add a bit of randomness, add a bit of noise to it, but it's the same thing. Same thing here. After a year of frozen relations between China and Australia, there is hope for thaw in the relationship. Wang Yi met with a delegation from Australia to mark the 50th anniversary. This is actually the same thing as this message. There is hope for a thaw in relations between China and Australia with China's foreign minister. So instead of putting in the name here, it says China's foreign minister. But it's the same idea here. There is no difference in the underlying message. It's just, slightly different vocabulary. So this is what I mean by actually caching the map side, but not caching the reducer side. So it feels a bit of randomness when your user is using your application. It feels like, hey, you're not actually just being lazy, trying to serve me the same content. You're actually trying to find new ways to explain the same fundamental underlying data. The last one here, Indonesia plans to produce a record 695 million tons of coal in 2023 and export 580 million tons. If you look at this one, this is the same thing here. Indonesia plans to produce a record 695 million tons, but here it gives you more details, but it's the same thing, right? So let's take a look. This one, instead of taking 7.19 seconds, it takes only 2.73 seconds, and it only costs 1 cent. So that's still better, right? So you save some money, you save some time, quite a lot of time, just by doing this partial caching, right? So you cache some part of this chain and not the whole thing. By the way, about this LangChain.db, if you actually have a SQLite extension in your VS Code, if you don't know how to do that, go and look at my video. I have a video on that as well. Generally just search for SQLite, right? If there is there, then you could use this to sort of open this up and explore that for a little bit. So I could just go ahead and say SQLite, open database. It's going to ask me to pick the one that I just created. So this is the LangChain.db. You can name it anything you want, but since I name it as such, I'm going to click enter. And now the SQL Explorer is going to open that up on the left hand panel, and you could look at the schema. You could just view on the variables in here. Now if this is a very huge database, this is probably what you'll be doing most of the time. You're not going to actually run the entire thing. But since this is not that huge, and I know it's not that huge because I created this and only to store a simple summary.txt. It's not a lot. So we could actually click on this button and it would say show table. And now this will bring up the entire show table. So let's take a look at this one, right? So here we see that initially we run this. So there are 4 different queries here. What doesn't fall far from the tree? Write a concise summary of the following, and then you see the different results here. And then the concise summary again, and concise summary again. So every time we run it, this is where the cache is going to be stored. So every time you ask the same stuff, if you say write a concise summary of the following, it's always going to return the same results here for you. And if you're building LLM applications and you're still not using caching, I urge you to give it another look and seriously read up about it. And if you have some use cases for it or you want to see me do a deep dive on, leave a comment below and let me know. If you have questions, also leave a comment and I'll see if I can help you out. Alright, that's all for today. Something incredibly powerful when you combine them with the other techniques that you pick up from this long-running LLM series. For a next step, I think you should check out the GitHub repo and watch the other videos in the series. I'll see you in the next one. Goodbye.